All right, this screencast is going to be on looking at what's inside the Earth. So in the earlier part of the 20th century, geologists studied vibrations or seismic waves generated by earthquakes to learn about the Earth's interior structure. So they discovered that it was made up of three distinct layers: the crust, the mantle, and the core. If you find here, the crust itself is this hard, rigid, outermost, thinnest layer, and it's only about 5 kilometers thick under the ocean, which is actually quite thin. But it's more like 20 miles thick or 30 kilometers thick underneath the continents. As I begin moving inside the Earth a little bit more, or toward its interior, you'll find that we find the mantle. And the mantle is divided into two regions, an upper and a lower mantle. So this is a semi-solid rock that's located beneath the crust, and it's about 1,800 miles or 2,900 kilometers thick. Here we have the outer core. The outer core is the only liquid layer of the Earth. This is a sea of mostly iron and some nickel. It's roughly 1,800 to 3,200 miles below the surface, and it's about 1,400 miles thick. So notice that the core has an outer core feature of liquid rock, and it has an inner core of an extremely hot solid sphere of mostly iron and nickel. And this is at the center of the Earth. And what we're going to be studying is how does this play out and lead to the Earth's magnetic field. And we're going to be calling this process of the dynamo effect. But while I have this animation live, you'll come to learn that the inner core is actually moving and it's rotating. And because it's just so hot, it's sending convection currents out into the liquid outer core. And these circulation currents are moving charged particles. And when you move charged particles around a solid interior core or a solid metallic feature, you generate an electromagnet. So the Earth's magnetic field is a result of what's called the dynamo effect. We have a solid metal core, and we have convection currents of moving charged particles outside of it, and together these represent or create what's called the dynamo effect. So the Earth's the magnetosphere, this is the Earth's magnetic field that's generated from the dynamo effect itself. The magnetosphere is an area of space around the Earth that is controlled by the Earth's magnetic field. So these are pictures that are showing the magnetic field. It's simply a location in space where magnetic forces are generated. And this is what the Earth's magnetic field looks like. We're presuming the sun is over here and the sun's solar wind is coming at us kind of in a northeast direction. The Earth's environment extends all the way from the sun to the Earth and even beyond. It is not an empty wasteland of space. Instead, the near-Earth space is full of streaming particles, electromagnetic radiation, and constantly changing electric and magnetic fields. All of these make up our magnetosphere. It is important to learn as much about this space around the Earth as we would any other part of the Earth's environment. The magnetosphere helps protect the Earth from the danger of the solar wind. The magnetosphere extends out approximately 10 Earth radii. One Earth radius is about 7,900 miles, so it's a pretty large magnetic field. So here's the dynamo effect, and I want to make sure we reiterate this process of what's going on inside the Earth. We've got the solid metallic core, and this is kind of the basics, the accepted explanation for a solid metallic inner core central to the Earth. But convection, that's these arrows here. We've got hot material rising and less hot material sinking, and that's simply a process of just like warm air rises and cold air sinks. It's the same concept here. So convection drives liquid outer core and it circulates relative to the Earth's magnetic field. So the Earth resembles an electromagnet where one gets the same effect by moving electric current around a metallic interior. The magnetic effects result from moving electric charges. So what we have here, here's the example of the electromagnet. If I wrap this copper wire around this metallic nail and I hook a battery to it, it's pushing current. So it's pushing charged particles around here, and I can actually create a magnet. It's the same effect, a solid metallic core with moving charged particles. So the dynamo effect is there in turn kind of very much like that of an electromagnetic process of moving charged particles around a solid metallic core. So here's a video that'll help reiterate that.
The sun is a star, like the other stars we see in the night sky. It's much closer though, so it looks different, like a gently glowing ball. But there's nothing gentle about the sun. Those dark patches are sunspots. Each of them is about the size of Earth. Sunspots look dark because they're the coolest places on the sun, only about 8,000 degrees Fahrenheit. The rest of the sun is even hotter. The sun's energy, like that of all stars, is created by collisions between tiny particles called protons. Every second, countless numbers of protons collide and fuse within the sun's core, releasing incomprehensible amounts of energy. Most of this energy leaves the sun as light. Some of it leaves the sun's surface in a continuous stream of charged particles known as the solar wind, which blows out into the solar system at almost 1,000,000 miles an hour. Or in less frequent but faster solar storms that blast particles out into space. We're looking at actual images of solar storms taken by a NASA satellite. See that static? That's a solar storm cloud hitting the satellite and overwhelming its imaging device. The solar wind blasts across the planets in the solar system every second of every day. It's so powerful that contact with it would sweep away a large portion of our upper atmosphere, removing much of our water and dramatically altering the development of life on Earth. But fortunately, Earth is protected by an invisible natural shield. What you're seeing is a visualization of Earth's magnetic field. This field arises from Earth's iron core, which makes our planet act like a big magnet, attracting some things and repelling others. Wrapped in this cocoon, Earth is sheltered from the solar wind. But some of the particles make it through this magnetic barrier, eventually reaching the North and South poles. The results are spectacular. Glorious, shimmering curtains of color. This one is the Aurora Borealis, the northern lights. Auroras occur when charged particles from the solar wind and solar storms collide with the upper atmosphere of Earth, causing atmospheric gases to glow. That's the International Space Station, circling the globe in low Earth orbit, about 250 miles up. Not many people have seen the aurora from out in space. The collisions that cause auroras happen between 60 and 300 miles above the surface of the Earth. Far above where airplanes fly. And create one of the greatest natural light shows on our planet.
So as a result of the Dynamo Effect, it is important that we understand the Earth's interior layers. So the crust, the mantle, which is subdivided in an upper and a lower mantle, and the core, which is divided into the outer core, which is a liquid, and an inner core that is solid metal. So as a result of this, the Earth generates a magnetic field. And if you look here at this picture, it's showing you that the Earth's geographic North Pole is actually the Earth's magnetic South Pole, and the geographic South Pole is the Earth's magnetic North Pole. So what we have here are field lines in space, just the forces that are able to be generated from the Earth behaving like that of an electromagnet. You'll find here that the field lines point from our geographic South to our geographic North, which tell us that the Earth's poles are actually kind of mislabeled. But it is still geographic North is Earth's magnetic South, and geographic South is Earth's magnetic South Pole.